Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, minimum number of operations to satisfy the conditions. We will also be discussing one harder version of this problem. This particular version of the problem is a well-balanced medium problem, similar to the last problem. Today's contest was really well-balanced. The harder version of the problem that we'll be discussing will have constrained grid ij less than equals to 10 power 9, and then m can be anything between 10 power 6. Obviously n cross m should be iterable, so n cross m should be within the limit of 10 power 6 to 10 power 7, right? So if you have to solve that problem, how you will approach that? So if you are here just for the follow-up, feel all the timestamps are there in the description below, so feel free to move to the section of your choice. Having said that, if you are not able to solve this or faced a bit of difficulty solving this during the contest, I would encourage you to watch the entire video to help understand the thought process, so that next time you are able to solve this by yourself. So with that, let's get started. The problem states that you are given a 2D matrix of m cross n size, and in one operation you can change the value of any cell to any non-negative number. Now you need to perform some operations such that each cell grid ij is equals to the cell below it and different from the cell to its right. So we'll return the minimum number of operations required to make this happen. So let's take an example. Let's say this is the grid, and let's talk about this particular cell. So for this cell, this should be equals to the cell below it. So this is actually equals to the cell below it, and this is different. This should be different from the cell to its right, and this is actually different from the cell to its right. So this cell satisfies the constraint. Let's talk about this one. There is nothing below it, so first condition doesn't need to be satisfied. For second one, there is one element in the right, and this is not equal, so second condition is also satisfied. So this cell is also good. Similarly, for this cell, this is equals to the one below it, and this is not equals to the one to its right, so this satisfies the constraint. Similarly, this one also is not equals to the right, so it also satisfies the constraint. And similarly for this one, this is not equals to, or this is equals to the one in the one below it, and there is nothing in the right, so second condition we don't need to satisfy. So this for every cell, these two conditions are satisfied, and hence answer here is 0, or rather minimum answer here is 0. We don't need to perform any operation to make it satisfy the constraints. Let's talk about one more example, 111000. So in this case, if you look at the first cell, this should be equals to the one below it, which is not the case, and this should not be equals to the one to its right, which is also not the case. So we have to do some operation for sure here. Now one possible configuration would be change it to 1, change it to 0, change it to 1. You perform 3 operations and change the second row of the first column to 1, first row of the second column to 0, and third column of the second row to 1. If you do this, all the cells will satisfy the given constraint, and you have applied 3 operations to make this happen. You can't apply less than 3 operations and still have the matrix satisfy the given constraint, and hence the answer here is 3. Now before jumping to the solution, let's try to understand, is it always possible to make the matrix compliant, or there are some scenarios where it can't be compliant? And if there are such scenarios, what should we do? Because problem statement doesn't talk about that. So the answer is, look at the operation. Operation is, in one operation you can change the cell to any non-negative number. That means that in the worst case, what you can do is you can change every cell of the matrix to your choice. So in a way, even if nothing works, one of the approach you have is you change every cell of the given matrix to a valid one, and in that case you will require m cross n operations to make the matrix compliant. So whatever is the case, because of the operation type, we are always able to make the matrix compliant, and hence there is no non-compliant state exist after the operation, and hence the problem doesn't talk about that, and we don't have to worry about that as well. So let's move and understand how to solve the problem. So first, let's try to understand these two conditions, and let's see if we can optimize this matrix a bit. because the first thing you should actually try is look at the operation and see if there are easy wins here. So let's look at it. First condition, grid ij should be equals to grid I plus 1j. So let's say this is the grid ij. So this should equals to grid I plus 1j. Now let's say this is grid ij. So this should also be equals to grid I plus 1j. This should also be equals to grid I plus 1j, and this should also be equals to grid I plus 1j. In turn, this entire column should be equals to a single value, let's say x, right? Now, because this entire column is equals to x, so does this column will be, right? This should be equals to some y, right? Now, with the first condition, we are sure that every column will be equals to one particular value. So that's what we get out for the first condition. Let's talk about the second one. Grid ij should not be equals to grid of ij plus 1. So basically this should not be equals to this. This thing should not be equals to this thing. Similarly, this thing should not be equals to this thing. This thing should not be equals to this thing, and so on and so forth, right? Now we know that entire thing is equals to x, and we know that this entire thing is equals to y. So do we actually need to check entire thing? The answer is no. We can simply check x should not be equals to y. So these two conditions basically says that every value in a single column should be equal, and that should not be equals to the value in the right column, right? If we satisfy this, these two conditions will satisfy for every cell in the matrix, right? Now let's say so what we have to do in turn, we have to simply fill up one particular, let's say, column. So we'll fill one row, and we fill something here, let's say x1, x2, x3, x4, right? And if we are able to fill this, we'll say this x1 belongs to all of the columns here, similarly, sorry, all of the rows here, similarly x2 belongs to all of the rows of the second column, x3 belongs to all of the rows of the third column, and so on and so forth, right? Now coming to the second condition, x1 should not be equals to x2, x2 should not be equals to x3, and so on and so forth. So basically we can boil down the problem to, instead of matrix, we'll work with an array, and we'll say we have to fill this array such that now two existing elements are equal. That's the only thing we need to worry about. If we are able to fill this entire thing with this with values, we are done, right? Now filling one value here has a cost associated with it. What is the cost? Let's say you are filling x1. So you are filling x1 in all these, you are filling x1 in this cell here, means that you are filling x1 in all these cells of this column. So how much operation you require? The number of operation required would be equals to number of cells which is not equals to x1, right? So let's look at it with a bit more complete example. Let's say this is the given matrix, right? And for simplicity, I have converted this matrix to something like this, right? Wherein we are saying that there is a, so first column has two distinct elements, 2 and 4. 2 occurs 4 times, 4 occurs 1 time, right? Similarly, second column has two distinct elements, 2 and 3. 2 occurs 4 times, 3 occurs 1 time, and so on and so forth, right? Now our job, so we'll not worry about this entire thing for now. Or rather, let's keep it here, but we'll work with this particular thing for simplicity, right? Now your job is to fill this particular array such that no two adjacent elements are equal. Now let's focus on the first element. What are the possible values here? Let's look at the constraint. Constraint says that grid ij should be less than or equals to 9. So obviously possible values here would be 0, 1, 2, 3 all the way up to 9. Those are possible values. Now what about after 9? Is it possible to fill anything after 9 or before 0? Before 0 you can't fill because operation doesn't allow you to make anything non-negative. So before 0 is gone. Now what about after 9? So is it possible to fill 10 here or 11 here or 12 here? The answer is, think about what happens if you fill, let's say, 11 here. If you fill 11 here, how many operations you need? You will need total, let's say there are r rows, so you will need r operations, in this particular scenario you will need 5 operations, right? Why? Because everything is between 0 to 9. So if you are filling something which is not between 0 to 9, you have to change everything. So in turn you are wasting 5 operations here, right? Now if you fill, let's say, 12 here, then also you will be wasting 5 operations. If you fill 13, you will be wasting 5 operations, and so on and so forth. So even if you have to fill something else apart from 0 to 9, it's best to just assume that you are filling X. Notice we don't care about the exact matrix at the end. So we will assume that we are filling some X here, and for all these X, we know there will be one cost which is 5 in this scenario, right? So if we have to fill something else, we will fill a dummy value here and assume that it will cost me 5, and this dummy value will be unique in the entire array, because or in the entire matrix, because matrix just have 1000 into 1000 distinct values in worst case. So you have the liberty to fill it with any value of your choice, right? So that's like what all we can fill. So we can fill anything between 0 and 9, and we can fill X, where X is a representation of a unique value across the entire matrix, right? So these are the 10 or 11 values you can fill in this column, right? So let's start with one of them. Let's say you decided to fill 2 here, right? You will fill all of them. Let's say you decided to fill 2 here right now. Now once you fill 2, what happens? You have to first figure out the cost, right? Because if you fill 2 here, that means that you are making this entire thing equals to 2, right? So if you have to make this entire thing equals to 2, you have to change this 4 to 2. Rest all are 2 already, right? So how many operations will require? You will require the number of operations will be equals to number of elements which are not equals to 2. So in this case, there are 4 elements which are equals to 2. So number of operations required would be 1. So by wasting one operation, by spending one operation, you are able to fill 2 in the first place. Now what is your job? Your job is to fill the rest of the array such that this element is not equals to 2, right? And let's say you fill 3 here, just an example. And if you fill 3 here, what is the cost? Cost would be number of rows which are not equals to 3. So you have total 5 rows, 1 is equals to 3, so you will be costing 4. Now once you fill 3 here, what is your problem? Problem is now you have to fill the remaining array such that this element, the first element, should not be equals to 3. So isn't the problem repeating? Every time we are solving that, okay, given an array, fill this array with some numbers such that the first number is not equals to some value v, right? Now once you fill something here, you will be having the exact same problem. Given this array, tell me how many or rather what is the minimum operation such that in which I can fill this entire thing such that the first value is not equals to v is equals to what you have filled here, right? So hope you can see the recursion here. So let's define the recursion formally. Let's say we have defined a function f that takes in an array and takes in what is the first element, or what can't be the first element, right? So whatever you have filled last can't be the first element, right? So this function will give you the minimum number of operations required to fill all the elements in this array such that the first element is not equals to last, this particular element, right? Now what you can do, let's say you are filling up you have to fill this array. This array, let's say, has a size of 7, right? So basically this is an empty array, so you can replace this array with a simply number which denote how many size of this array it is. So you have to fill the size of array 7. So what you are doing, you are just filling up the first element, right? And what you can fill here, we have discussed already. You can either fill 0, you can fill 1, you can fill 2, all the way up to you can fill 9, right? And finally you can also fill x here, where x is a representation of any unique number. Now if you fill 0, number of operations required to fill 0 here would be number of 0 you had at this column, at the current column, r minus that will be the number of operations required, right? And this is to fill the first row, or rather the first element of the empty array. You still have to fill the rest of the element. So for the rest of the element, you will say you still have 6 empty spaces. The first space should not be equals to 0, because 0 is what you have filled at the current space, right? So this will be the cost if you choose to fill 0 at the current place. Similarly, if you choose to fill 1 at the current place, or at the first place, number of operations required would be r minus 1 plus f of 6 comma 1, right? Similarly here, r minus 2, count of 2, right, in that particular column, plus f of 6 comma 2, right, and so on and so forth all the way up to x, right? So in this particular x, you will be simply saying r minus 0, which is r, plus f of some number which doesn't denote anything. Let's say minus 1 comma 6 comma minus 1, right? Basically you can fill anything afterwards, because whatever you have filled here is a unique element across the array, right? So you can fill anything here, and anything is represented by minus 1. So hope this particular recursive state is clear. So what you need the value of f of 7 comma minus 1 in this scenario. Either you call it 7 comma minus 1, or you call it 0 comma minus 1, depending on how you denote how many elements are left. So if you directly put 7, you are saying that 7 elements are left. If you put 0, you may say that, okay, I have 7 minus 0 elements left to be filled, or rather I have filled everything before 0 and I have to fill everything after 0. So your choice. You have to do the conversion yourself. This will be what you want, and you know how to compute the state ij, because what you'll be doing, you will be simply putting the value at the first column, and you will defer the rest of the thing to the same function again, right? So hope this entire solution, this entire recursion is clear. If it is not clear, I'm not doing the dry run, because that will make this video too long. We have to discuss the other part as well. So for now, I will encourage you to rewind and watch that section again. If you still didn't get it, try to do a dry run using a pen and paper, and feel free to post an image down below if you want, if you still have doubts and you want me to look at it. So what will be the pseudocode? The pseudocode would simply be what we just discussed here. We have a function that takes in 2 arguments, one index, and second what we have filled last, that is what we can't fill at the first position of this array. Now this index can be 2 things, as we discussed. Either it can be how many elements are left, or it can be which index I am currently filling, right? So in this particular scenario, I have assumed that which index I have currently filling is what my index is, right? Now at this index, we can't put last, but we can put anything else, right? So we will simply, these are the best conditions, we will come to that. So we will simply put everything between 0 and 9, and if except last, so I think I missed this, so except last, I will try to put everything between 0 and 9, and what we put at index can't be put at index plus 1. So we'll simply say, if we put index here, what are the operations required? Operations required would be number of rows minus frequency of index, frequency of val at the index column, right? So this you can build beforehand. Similar, this is actually equals to this, which will help you calculate the number of operations required efficiently. Now this is the number of operations required to fill some val at this index. Now you still have to fill the rest of the element, or rather you still have to fill everything starting at index plus 1. So we'll simply say I need to fill everything starting at index plus 1 such that the first element is not equals to val. So give me the number of operations required, right? And apart from all of these, you can also fill x here, which is f of index plus 1 comma minus 1. You can fill that as well, but this is not required. Why? We'll come to that in the next section, but you can try that, because if you don't want to prove that, you can simply put a -1 or any reference value of -1. In this case, it can be -1 or it can be 10 as well, because you know that 10 can't be put. So it's your choice. So you can put anything which refers x, and if it is x, this last will not be subtracted from the given list. You can put anything between 0 and 9 there, right? So this is the overall algorithm. What will be the time complexity? First of all, we need to do memorization, because the same state we may end up computing the same state again and again. For example, let's say you put 2 here, and now you are saying that, okay, starting at 1, I need to fill everything such that the first element is not equals to 2. Now let's say you put 5 here. So what you're saying is, okay, starting at 2, tell me the minimum number of operations required to fill everything such that the first element is not equals to 5. Now let's say after some iterations you pick 4 here, right? Now if you are picking 4 here, you'll say, give me the minimum number of operations that is required to fill everything starting at index 1 such that the first element is not equals to 4. Now let's say you again pick 5 at index 1, because 5 is not equals to 4, right? So that is one valid choice. So you can say, give me everything starting at give me the minimum number of operations to fill everything starting at index 2 such that the first element is not equals to 5. So in this scenario as well, you have to compute f2, 5. In other scenario as well, you have to compute f2, 5. So better to compute it once and store it and reuse it if required, right? So what we have done, we have simply created a 2D array that will be initialized with -1, and if it is not -1, it means it is computed before, and we'll simply return it, right? So we are computing each state exactly once, and inside each state we are doing some constant operations here, and we are iterating over 0 to 10 here. So we are doing almost order 10 number of operations, where 10 is the size or number of distinct elements in the grid. So let's call it distinct element in the grid, multiplied by, in this case, distinct element in the grid is just 10. So d is equals to 10 for this particular scenario, multiplied by number of states. How many states you have, or rather how many different ways this function can be called. Number of different value of index, that can be anything between 0 and n, multiplied by number of different values of last. So this can be anything between 0 and d, right? So the number of states would be equals to n into d. So overall complexity is order nd square, right? So this is the overall time complexity of this entire algorithm, and this will fit in the given constraint, because value of n is just 1000, right? We are just iterating over all the columns, and number of distinct values just 10. So 1000 into 10 square, which is very small, to simply pass the given time constraint. So you can implement this and it should pass the given time constraint. Now I'm not showing the code for this because this is very straightforward. Let's directly jump to the follow-up, which is slightly harder. Basically it says that instead of nm equals to 1000, you have nm equals to 10 power 6, and grid of ij is less than equals to 10 power 9. Now obviously n cross m should be also less than equals to the same number, because otherwise you can't even iterate over the entire array, right? So assume that it's there. The only motive to show that here is basically you don't need both n and m, you can still work with one of them, right? So you need to solve the exact same question with this particular constraint. How to do that? Notice if you follow the exact same algorithm, that will not work, because the number in a row can be anything between 0 and 10 power 9. So either you need to iterate from 0 to 10 power 9, or you may say that, okay, there can be at max 10 power 5 distinct value in a particular row or in a particular column. So why even iterate over all 10 power 9? We can just iterate over 10 power 5 distinct values. That's also fine. Even 10 power 5 will not pass, because this entire thing will come here as well, and you can't afford to have n d square complexity, right? So you need to optimize this for sure. So there are two things to optimize. First of all, you can't afford even a single D here. So even you can't afford this last, and you can't afford this loop as well, right? So as always, removing anything from the DP state itself is something which requires you to rethink your complete approach. So let's park that for now. Let's see if we can optimize this particular thing, right? Now, if you want to optimize this particular loop, there are two things. Either you somehow make an observation and say that, okay, you don't need to iterate over this entire loop, and maybe you can say the optimal value would be X or Y or anything like that. Or you say that, okay, everything in like you make some observation and you will say optimal value, you don't need this loop, and you can compute this entire thing with some range query or something of that sort, right? So let's try to see what's happening here, or what are the values required here, and then if that doesn't work, we'll try to convert it to convert this to bottom up and see if we can apply some range queries there, right? So in this case, let's assume that in the optimal scenario, again we're talking about the optimal scenario, this entire thing is x1, right? And this entire thing is x2, right? And this column, the middle column, has 5 distinct values: x1, x2, x3, x4, and x5, right? And also assume that there are 12 rows here. So number of rows in this particular matrix is 12, and x1, number of different x1 is equals to 5. Number of times x2 occurs in this particular column, let's say, is equals to 3. Number of time x3 occurs in this column is, let's say, equals to maybe 1. Number of times x4 and x5 occurs, 8, 1, 9, and then 3, right? So let's make it 2, 1, and 1, right? So these are the like frequency of x1, x2, x3, x4, and x5 across this particular middle column, right? Now, what you will put here, in best scenario, you would want to put x1, right? Why? Because that would lead you to minimum cost, because there are already 5 rows with x1 value. You just need to change 7 more rows to make it all equal. So if everything is in happy, you would want to change it to 5. You'd want to change it to x1, right? But let's say we are saying that x1 is already existing in the previous row. Again, we are talking about the optimal scenario. So let's say x1 already exists before. So now what's the second best choice you have? You will try to put x2, right? Because x2 now occurs 3 number of times. So if you put x2, you need to change only 9 rows. Now we are saying that in optimal scenario, x2 can occur here afterwards, right? And this should not be equals to this as well, right? So x2 is something we can't put here as well. Next choice is x3, right? x3 is equals to 2. That means we need to change 10 rows in the worst case. Now x3 you can put here, right? Now, do you even need to care about x4 and x5 in any scenario at all? The answer is no, because even in the worst scenario, your third best option in this row would be the one which you will want to put here instead of fourth or fifth best option. This fourth or fifth best option will never be an optimal choice for this particular column, right? Again, just to repeat, we are saying that this column should not be equal to the previous one, and this column should not be equal to this one. So in worst case, what would happen is whatever works optimal for this row, for this column, might be an optimal choice for the previous one, and whatever is the second optimal choice might be an optimal choice for the next one. So whatever is the third optimal choice is what you will put here. You will never go for fourth and fifth, right? So in other words, what we are trying to say is we can completely skip x4 and x5 or anything after that, right? So if there are 10 power 5 distinct values, assume that there are total x 10 power 5 different x here, and let's say everything has equal frequency. So let's say there are total 10 power 5 rows as well. So everything is equals to 1, right? So what we are saying is, or rather, let's take a simple example first. Let's say there are total 10 power 6 rows, and this is the highest frequency, this is second highest, this is third highest, and these are all the fourth and fifth highest, right? And there are no ties, right? So first, second, and third is unambiguous. Others may have ties as well, but we don't care about them. So in this scenario, what we'll say is only thing that we would try at this column would be x1, x2, or x3. So instead of trying out everything between 0 and 10 power 5, we'll just try out x1, x2, or x3, where x1, x2, and x3 are the top 3 highest occurring element in that particular column, right? Now, some of you might be thinking, okay, that's good. Now, what about there is tie? Let's say everything has equal frequency, 1, 1, 1, 1. Now, which one will you choose? I would encourage you to pause and try to think. Hope you thought about it. The answer is, it doesn't matter. You have everything equals to 1. So whatever you put here you will need to change exactly the same number of rows in all the scenario. That is r minus 1. If r is the total number of rows, you have to change r minus 1 rows in all the scenarios. So in this scenario, it doesn't matter if you pick x4 or x5 or x3, you'll just pick any 3 of them and try it here, right? Because in worst case, again, whatever you want to put will be one of these, like will match one of the other twos, and third one you will choose, right? So in Crux, for a single column, we don't want to, or we don't need to try more than 3 distinct values. So this entire 10 power 5 thing will go away with just 3 distinct values. So this entire thing is almost constant. So whatever we are doing inside each state is almost constant, order 1 operation, right? Now, what is the complexity? The complexity would be still index into last, like number of different states. So index is n and last is d, because even though let's say you are putting x1 here, x1 can be up to 10 power 9, right? That is not something which will change. So overall complexity is not nd square, rather it is nd with this optimization. But still nd is very huge. We can't afford that because n is 10 power 5 and d itself is 10 power 9. So we can't afford that. So we need to optimize that as well. Now from here, optimizing is very, very straightforward. So I would encourage you to again pause and try to think by yourself. So notice that you are only putting x1, x2, or x3 for a particular column, right? So let's say you are talking about column C, right? Now, when you call C plus 1, f of C plus 1 comma something, this something can either be x1 or x2 or x3. It can't be anything else, right? Similarly, when you will call for C plus 2, let's say, it will either be y1, y2, or y3. So it will not be x1, x2, or x3, but rather y1, y2, y3, because this can be the top 3 values in this column can be completely disjoint from the top 3 value in this column, right? So basically for each index, you are sure that there will be 3 distinct value of last. But what would those 3 distinct value will be is something you are not sure, right? So either you can like do a mapping and ensure that, okay, if you pass 0 here, you're talking about the first largest value in this list. If you pass 1 here, you're talking about the second largest value in this list. If you send 2 here, you're talking about the third largest value in the list of index minus 1, right? Again, you're filling index. It means you have to skip this one, which you have filled in the index minus 1. So either you pick 0, 1, 2 with a mapping, or you can change this array to a map, and that will solve the purpose, right? So overall, even though it look like it will be 10 power 9, but not all of them will be exercised. Every time only 3 of them will be exercised for a particular index, and hence this entire thing is just order n into 3, which obviously is just order n, where n is simply the number of columns we have, right? So hope this entire thing is clear. If it is clear, I would strongly encourage you to pause and try to code this entire thing by yourself. You can use the same test, or you can submit the solution in the same problem, because that's just an optimization of the same problem. So same test case, if entire test case would pass, that is a good indication that your solution is almost correct, right? Now, if you still have some doubts, let's look at one small dry run before we look at the code, right? So again, firstly, let's prepare this map out of this matrix. This time we have 6 rows and 7 columns, and we have also sorted it by their frequency. So 2 occurs 3 times, 4 occurs 1 times, 3 occurs 1 times, and 5 occurs 1 times. This is all for the column 1. Similarly for column 2, 2 2 2, 2 2 1 1, and so on and so forth. Now, as per our theory, what we know that we will only care about the top 3 of each of them. So we can simply erase anything afterwards. So we'll not worry about any of this. So let's simply cross this out. We'll not work with this, and we'll work with only the above ones, right? Now let's make it 0 1 2, and this is our indexes already, 0 1 2 3 4 5 6, right? Now when we say f of 2 of, let's say 2, that means second index of the first column, or the first or the first column. So for the first column, what is the second index here? That is 4. So basically we are putting 4 here, we'll not put 4 here, right? That's what we have meant, but that's what we meant here, right? So I assume that you will be doing this mapping by yourself. So for now, we'll not worry about this mapping. We'll simply call it f of index comma last, where last will be the last thing that you have put in the previous index, right? So we have to fill this entire matrix, right? So let's talk about this 0 1, 0 index first. So what are the possible choices here? You can either pick either fill 2 here, or you can pick 4 here, or you can fill 3 here, right? So there are 3 possible choices. Either you will put 2, or you will put 3, or you will put 4, right? If you put 2, you have already 3 columns or 3 rows equals to 2, so extra operation required would be 3. If you pick 3, you have 1 column which is already equals to 3, so you will require 5 extra operations, and similarly for this one also you will require 5 extra operations. Now let's start with the first one. When you pick 2 here, you will want, I need to fill everything starting at index 1 such that the last value is or the first value is not equals to 2, because 2 is what we have filled just before this. So now at 1, you have 3 choices. Like let's say you are computing f of 1 comma 2, right? Let's forget about all of this, because f of 1 comma 2 will come when you are expanding this, right? Now here you have now 2 choices. You can fill, again, first of all you had 3 choices, 2 3 or 4, but because you have already filled 2 here, you can't fill 2 here, right? So you have 2 choices. Either you can fill 3 here, or you can fill 4 here, sorry. So if you fill 3, number of operations required would be total there are 6 rows, so 2 of them has 3, so number of operations required would be 4. Similarly for this, number of operations required would be 4. Now again, you can either go from this route to let's just visualize this. Let's say you are trying to figure out f of 0 comma minus 1, right? So from there, you know that you can either go to f of 1 comma 2, or you can go to f of 1 comma 3, or you can go to f of 1 comma 4, right? If you go to f of 1 comma 2, you will require extra of 3 operations, right? If you go to f of 1 comma 3, you will require extra of 5 operations, and similarly if you go to f of 1 comma 4, you will require extra of 5 operations, right? Now we are trying to expand f of 1 comma 2. So from 1 comma 2, we know that we have to fill everything starting in index 1 such that the element should not be equals to 2. So here we have only 2 choices. We can either fill 3, or we can fill 4, because others we know that we will not fill, we'll only fill one of these 3. and 2 we can't fill because 2 is something we have already filled. So if you fill 3 here, you will say starting from 2 I need to fill everything such that the first element should not be equal to 3. Similarly, if you fill 4, then you will say starting at 2 you need to fill everything such that the first element is not equal to 4. Now if you choose this route, you have to require some extra operations at index 1 which would be equals to 4, right? Because 2 of them is already 3, so you need 4 of them to be equals to 3 as well. So if you go this route, you will require 4 extra operation. If you go this route, you will require 4 extra operation. Now similarly for f of 2 3, you are saying that starting at 2 you need to fill everything such that the first element is not equals to 3. So at 2 there are 3 possible choices, 1, 2 and 3. You can't fill 2, so you have 2 choices. Sorry, you can't fill 3 here, so you have 2 choices, 1 or 2. So you'll say starting at 3 I have to fill everything such that the first element that you have filled is 1. Starting from 3 you have to fill everything such that the first element you filled is 2. And notice you can't go to 3 3 because 3 is something you have already filled, right? Sorry. And if you go this route, you will require an extra operation of extra 4 operations, right? And similarly for this one as well, you require extra 4 operations. If you keep on doing this, let's say f of 3 1 is 5. Assume that you expanded this and you get 5 here. F of 3 2 is let's say it is 9. Assume that. So overall you are saying that you will require 9 operations, 5 plus 4 9 operation to fill everything starting at 3 if you are trying to fill 1 at index 2. Similarly, you require 13 operations if you fill 2 at index 2 to fill everything starting at index 3. So of 9 and 13, 9 is the smallest one, so you will say f of 2 3 is 9. That is, starting at index 2, if you need to fill everything, you will require 9 operations. Similarly, you will get something for f of 2 4 as well. Let's assume that it is 8. So in this case, you will say you require 13 operations to fill everything starting at index 1 such that you have filled 3 at the first index. And similarly, if you require 12 operation to fill everything starting at index 1 such that you fill 4 at the first index. And among these two, 12 is the minimum. So you will say 12 is the value of f of 1 2 and so on and so forth. So finally, you will get the value of f of 0 1, 0 minus 1, which will say what is the minimum number of operations required to fill everything starting at index 0. And that is something which you want, right? So hope this entire algorithm is clear. Let's look at the code. Again, if you have watched this point, strongly encourage you to pause and try to code this entire thing by yourself. So coding will involve 2 pieces. One, figuring out this entire matrix and figuring out the top 3 of each of them, right? That's the first piece. Now once we have done this, the rest is straightforward. We just need to apply the operations step by step. So we can simply replace this for loop with a simple list from that except the last one, right? Now what I am showing you is the bottom up solution of the same problem, but you can code this entire thing in top down as well, and that will also pass, right? So first we are building this matrix where we want to find out top 3 for each of the indexes. Now there is small edge case which I intentionally left while explaining, is that what if the column doesn't have 3 distinct values at all, right? So that I will leave it to you how to fix that. So hope you actually thought about that as well before looking at this particular solution. So what we are doing, we are figuring out the map. We are building a map for each column of all the element frequency. Now we are checking if the number of unique element is less than 3, we are pushing some extra elements. And notice what we are pushing is something that doesn't exist in the original array. Notice the original constraint was everything is less than equal to 10 power 9. So we are putting some values which doesn't exist at all, right? Now these are just representations. This can be anything at all, this can be any number at all, right? So we put at this stage, we have ensured that after our frequency array contain at least 3 distinct elements. So now that we know that, we'll simply put all the elements and their frequency in a vector and sort it. we only care about the top 3. Now, because this sort is smaller to larger, I simply separated the row count here so that we know how many exact operations are required. Instead of figuring out afterwards, I simply calculated it now. So the one which require minimum operation should be in the first. So we'll simply take the first 3 elements here. Again, I think this min was not required anymore. I think that was something which I had during the contest. So now this is the top 3 elements you will take and add it to your final map which you are maintaining, right? So every vector or every position is a map which contain this two information: what is the element and what is the frequency, or rather in this particular scenario, what is the number of operations you need to perform, right? Now once you have this map built, we simply need to fill every column one at a time. So we start from 0. We'll say these are the 3 distinct values that can come at 0 or at column C. Now we have to figure out what we need to fill among these 3 distinct. Let's say you are trying to fill val here, one of these 3 distinct values. So for this val, you need to understand what is the total number of operations that are required, right? Or in other words, whether this val is something you have filled before or not. So that's where we simply iterated over what we have filled in the previous iteration. So dp is also a map in this scenario. So what we have filled in the previous iterations, if that is equals to val, we'll simply continue, otherwise we'll take the minimum, right? Now after this iteration, we will have answer or the minimum number of operations required if I start with val at the current position. So if I put val here, I will require these many extra operations. So this is the total number of operations required if I put val here. So similarly, I will do the same for all the different values here and reset our dp to the new dp. And once we do all of these, the last, after entire thing, it will contain the last dp, or whatever dp will have will contain the state for the last row or after pressing the last row. So we'll simply iterate over all of them and take the minimum across all of them. So that is the answer. Again, this was the bottom up approach of the same solution top down. You can code this entire thing in top down as well. This is just what I ended up doing during the contest. So hope this entire solution is clear. If you have any doubts in either the first version or the second version of the problem, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.